Hi, consider the initial value problem, y prime is equal to 2y. The analytic solution is given because this is a non-linear differential equation. We start with A, approximate y at the x point 1 using one step in Euler's method. So we know the step is going to be 0.1 because if we have to get at an x of 0.1 in one step from 0, and we start at 0x, at x equals 0 here, the only way is to have a step of 0.1. So now, what is Euler's method? Well, Euler's method, I showed it to you in a previous video, but basically what it's saying is that the new output is equal to the previous output plus a function of the slope at x and y's at the previous x's and y's, and I'm gonna just write 0 here for the first one just to make it a little bit cleaner. So this is 1 0 x0 y0 times h, which is our step. Well, actually the step comes from a different place, plus x1 minus x0. Now, this x1 is really x0 plus h. So then we have our minus x0 here. And so what happens? Well, it happens that these cancel out. And so we can write y1 is equal to y0 plus h times f of x0, y0. So that's what we're going to do. Our y1 in this case is going to be equal to our first y plus our step, which is 0.1, times the expression of the slope evaluated at our previous y, which is 2y. So 2 times our previous y, which is 1, we get a solution of 1.2. Now, if we were to evaluate the actual, that would be e to the 2 at 0.1. This is the actual solution. So if I input the x, it's going to give me the actual value of y. And that turns out to be 1.2214. Okay. And that is something that they ask later. I just went ahead. Approximate using and find a bound. Compare the actual error of y1 with your error bound. So the actual error is going to be the absolute value of 1.2214 minus 1.2, which is equal to 2.2214. Now, so we actually did part of part C. So now what I want to do is find a bound for the local truncation error. So to do B, you kind of need to know, or need to know where to find it, that the bound for Euler, the upper bound for Euler's method is y double prime of c times h squared over 2 factorial. So we have to take the double derivative of our function y of x, they told us, is e to the 2x. So if we take the double derivative of that, we get what? Well, the first derivative is going to be equal to 2 e to the 2x. The second derivative is going to be equal to 4 e to the 2x. So now we can say that this is equal to 4 e to the 2x times and the step is 0.1. We need to square that, divided by 2 factorial. And then we need to decide what to input here. And this really becomes with respect to c. So it's now a function of c because we inputted c into our function. Now, if we want the upper bound, we would put the highest value of x that we got, which we stopped at 0.1. So we'll put 0.1 in there. So we get 4e to the 2 times 0.1 times 0.1 squared divided by 2 factorial. And what we get is 0.0244. Okay, so this was our error from approximation. And so from this, we can say, looking at these two, we can say, well, let me just underline it like this. We can say that 0.2214 is and I realized I made a mistake. The error had a 0 here. So this one had a 0. Okay, that makes more sense. So here, 0.0214 is less than 0.0244, where this is the maximum possible local error. And so, yeah, because this was an expression for the upper bound, which is a fancy word to say the most amount of error that we can have. And the actual amount of error was less. So that one was find a bound for the local truncation error, compare it. So this was also C. And then what else? Approximate y of 0.1 using 2 steps, Euler method, and verify that the global truncation error for Euler's method is OH by comparing the errors in part A and part D. And we will do that in the next video.